Alright, so we're continuing with our SIR model. The original model was up here with the three equations, these three equations here, or we could use the shortcut version. In the homework, you should use the three equations, and in fact, the equations we're going to use are coming out of homework problem number 1, where we actually rescale the problem so that the population is actually 1. And so it's really a percentage of the population that we're working with. Okay. Um, so what I wanted to do in this video was talk about some of the parameters that you're looking at here, the beta and the gamma. There's only the two here, but then there's a parameter that's always discussed in the news, and that is this R0. Um, so let's see where these come from. So the value of gamma is actually going to be the average period of infectiousness. Average period of infection. Is infectiousness a word? So just as an example, if it takes 3 days for the infection to run its course, my headphones are falling off. If it takes 3 days, for the infection to run its course, then we would say that gamma is 1/3. Okay. Now similarly, beta is going to be the rate of infection, right? Because that's, let's go all the way to the top here. Nope. Actually, beta's here. Beta's here. Okay, so beta is going to tell us that's the rate of infection, which means what? Let's do an example. So suppose an infecting contact is made on an average every 2 days. Then beta would be 1/2. Okay, and so that's a little bit odd. Well, we'll talk about the kind of the units of all of these later on. But right now we can just kind of get a general feeling for what these are. So beta, you can see if the infecting contact goes down, like if it's every day, 3 times a day, you can see that this beta would really become large pretty fast, right? And that would be bad, right? Large beta means that S is moving down fast. Okay. Alright, so then the last one we wanted to talk about was the R0. And I guess before I do that, let's think about what happens at the beginning of an infection or beginning of a pandemic. At the beginning of a pandemic, if you look at this equation right here, S is approximately equal to N. Right, so this is a fraction right now. And so these would cancel each other out. And so you'd be left with saying that I prime is approximately equal to beta minus gamma times I. Right, now if this number right here is greater than 0, what does that mean? That means that your number of infection is increasing, right? And so that is what leads to an epidemic. So we can say that, just generally speaking, if beta minus gamma is greater than 0, then I of t increases. Okay. So now that we kind of have a feeling for what the relationship between beta and gamma is, the basic reproduction number, or reproductive number R0, is actually defined to be beta divided by gamma. Okay, and so the idea here, what is this? If beta minus gamma is greater than 0, what does that mean? That means that beta is greater than gamma, and so that means that if beta over gamma is greater than 1, we're going to have a trouble, right? And so that is R naught. So if, we could say right off the bat here, if R naught is greater than 1, we have an epidemic. Okay, and just to give you an idea of some of the values of R0, there's a bunch of these on the internet. I've written some down in your notes just so you can get an idea of what we're talking about here. Something like measles is very infective. 12 to 18 is the R0, and that's one of the higher ones. Polio, which was very infective, I don't know where I got that, infectious, has an R0 of 5 to 7. COVID-19, what we're experiencing right now, has an R0 that's been estimated to be between 3.3 and 5.7. While a seasonal flu, for example, just as a point of comparison, seasonal flu, and we all know how fast that goes around campus, right? Has a R0 of about 0.9 to 2.1. Okay, so there's kind of a wide range there because there's lots of variation, but you can get an idea of kind of where the R0s come from. So you can see here, measles is really a bad thing, right? Because the infection spreads very rapidly. And COVID-19, of course, is it spreads very rapidly itself. And so, yeah, we'll have to keep an eye out on when you're watching the news. They'll often report what the R0 number is that they're estimating for some of these things. Good. All right. So we want to try to analyze the solutions to our model. So what do you think the solutions will look like? So what should the S of t be? What should what should it look like somehow? Let's see, for the susceptible population, remember that the susceptible population is the initial population, and it's only losing numbers, right? It's not gaining any numbers at all. So the susceptible population, we expect it to just drop. It may not go to 0, it may drop to some number, but it is just going to be dropping. It's not going to be increasing, right? Because we're not making any allowances for S of t to increase, right? Good. Similarly, what happens to the recovered population, R of t? Well, for the recovered population, we expect it to start at 0, right, and then just work its way up. And then we expect it to level off at some point. These don't have to be the same. This could be coming up like that, for example. And then the infected is actually going to be n minus these two, the sum of these two, right? So if you think about that, then the infected is going to, well, it might have a bump, a maximum number, and then come back down. Okay, and so this is kind of what we expect to see. This is our I. This curve up here was our R, and this curve down here was our S. Now they may not look exactly like that. In fact, the I we saw, or we will see in some of the simulations, it may just come straight down. And so in that case, right, the R wasn't strong enough, you could say. The R0 was not strong enough. By the way, this R0 is not the same as this R, right? This is recovered. and this is, what did we call it? The reproductive rate. Okay, good. And so we're going to make some simulations and take a look at some of these curves in MATLAB. And so I've got another video after this that will show you how to do that. And finally, I just wanted to mention the linearization. And so this is going to be part of the homework, but I'll just make a note. So when we do the linearization, we can go ahead and use the reduced number of equations. So we're working with two equations. So if we have s prime is equal to minus b I over n times s, and I prime equals beta I over n times s minus gamma times I. Okay, where's the equilibrium solution going to be? Well, for the first equation to be 0, I equals 0, or s equals 0. So if I equals 0 in the first equation, then you can go to the second equation, and then that forces s to be 0. So this would give us a solution of 0, 0. And if s is 0 in the first equation, what happens? Oops, wait a sec. That's actually giving me the same solution. So let me erase that for a sec because I want to factor the I out of this bottom one. Right, and then I would be left with beta times s over n minus gamma. So I pause there for a second because if I is equal to 0, right, that zeroes out both of our equations. And so s is really free to be anything. And so we're going to consider two special cases. So if I is 0, s is free. Right, and so two special cases of that we want to consider are when s is equal to 0 and when s is equal to n. Okay, so when s is equal to 0, then we would be at 0, 0. And then for the other equilibrium, we would be at n0. You kind of think of it as an equilibrium. 0, 0, right, means that this is when r is equal to n, and so this would be after the pandemic. And if we have n 0, what does that mean? That would be the disease-free, right? And so these would be our among our equilibria, because really if I is equal to 0, right, then s could be anything. Okay, and so we're picking out the two extreme cases of s to take a look at those two in particular. And so in the notes, you'll see that we take a look at when, let's see, what do we linearize around? The disease-free version is the one that's being linearized in the notes. All right. So I'm going to leave that here. And so take a look at the notes, take a look at the homework. I've also got another video that goes through a numerical solution, and I'll talk to you later.